In this video, we're using integration by parts to compute the integral x natural log x. And we're going to do this in two different ways. One of them I would call the wise way to do it. The other way is what I would call the instructive way to do it. So it's definitely not the wise way to do it. It's very long by comparison, but we actually learn a really cool trick along the way. So what's the wise way to integrate x natural log x? The best choice when we use integration by parts for our function u is going to be natural log x because the derivative of that produces a way simpler function. So if u is natural log x, du is 1 over x dx. And to give you a sense for how you can make this wise choice more consistently, anytime you can turn a transcendental function like natural log into an algebraic function like 1 over x, that's going to be a big advantage for simplifying your integral. So we've chosen u equals natural log x, du is 1 over x dx, dv is the remaining part of the integral, which is just x dx, which means v is the antiderivative of that, which is 1/2 x squared. Now we apply integration by parts, so this integral turns into u times v, that's 1/2 times natural log x times x squared, minus the integral of v du. And v is carrying a factor of 1/2, which we might as well move out in front. And the rest of v is x squared, and du is 1 over x dx. One of those factors of x cancels. So for the integral part of this, and I'm going to go ahead and rewrite the first term as x squared natural log x. It just looks more natural that way. Now for the integral, I have the integral of x dx, which gives me a 1/2 x squared plus c. And then we just clean things up in one final step. I have 1/2 x squared natural log x minus 1/4 x squared plus c. Now let's take a look at what I've generously called the instructive way to do the integral. In this approach, we let u equal x, and the motivation there is that I know the derivative of u becomes simpler, but the trade-off isn't that wise because I have to find the antiderivative of the natural log of x in order to find v. Fortunately, I was given a hint in this problem. If you don't remember the antiderivative of natural log x, well, that turns out to be x natural log x minus x. So we set to work on the integration by parts here. If u is x, then du is dx, and that's a good thing. But if dv is natural log x dx, then v is going to be x natural log x minus x. Well, that thing just got a lot more complicated than the original. We can still apply integration by parts, and I take u times v, that's x times x natural log x minus x, minus the integral of v du. That's the integral of x natural log x minus x dx. And we start to clean things up here. I have x squared natural log x minus x squared. And then if I look at my integral portion, this breaks into two integrals. One of them is this negative integral of x natural log x dx, and the other is a positive integral of x dx, which gives me a 1/2 x squared. So now I have x squared natural log x minus x squared plus 1/2 x squared minus the integral of x natural log x dx. And the reason this approach is so instructive is this is one of the rare cases where we have to use what I would call the looping trick for integration by parts. What we just discovered on the right-hand side is a negative copy of the original integral. So one way to make this clear is to just give the original integral a name. We can call it I. And that's the thing I've been computing all along here. So this is I. It's x squared natural log x minus x squared plus 1/2 x squared minus another copy of I. And so what we do is add that copy of I to both sides of the equation. And I end up with a 2i on the left-hand side. On the right-hand side is all that junk that was out in front. X squared natural log x minus x squared plus 1/2 x squared. I'll go ahead and simplify that now. That's minus 1/2 x squared. And now I can solve for my original integral I. That's what we're trying to get in this problem by dividing both sides by 2. And this gives me a 1/2 x squared natural log x minus 1/4 x squared. Don't forget to put a plus c on it for this indefinite integral. And we get the same result. Now, even though you might complain that the path to the answer here was suboptimal, it is worth practicing that looping trick because sometimes it's unavoidable. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.